Hello, we are going to start on static equilibrium today. Static equilibrium means all the forces at all the particles of the system are separately equal to zero. So, for instance, I have a system is one particle system. It's the simplest thing we can think of. Say you have an electron, just one particle, then that particle can have multiple forces. Electron can have a gravitational force and electrical force. You can have a magnetic force, right? So uh, there are, say, various forces on this particle. Maybe this is F1, F2, maybe F3, etc. Okay. Now these forces are, if this is one particle, all of these are from outside. So they're all external forces. So this one particle system, all the forces are external. So if I, by equilibrium of this system would mean its acceleration has to be zero. So this particle cannot accelerate. So if this is acceleration zero, would mean acceleration zero would mean I add up all these forces in a vector way, and that should end up to be zero, however many forces there are. So if this was happening in one, if this was happening for, say, one line, so if there's some force F1 and there's only two forces, one pulling this way and pulling that way, if this to be equilibrium, this to be in equilibrium, this must balance those forces. That's what static equilibrium means. In this situation it will be F1 is minus F2, minus because it's in the opposite direction, right? If the situation was in two dimension, say if you was in a plane, say XY plane, and I have this one object, some F1 is this way, F2 is that way, F3 is that way. These will all balance, meaning if I add these two, it's exactly opposite of that guy. So if I add these two, I get exactly that guy. Okay, so F1 plus F2 plus F3 has to be zero because this acceleration is zero. This is what this was guarantees the forces have to be equal to zero. So this is for one particle system. What if I have more than one particle? Well, where would the equilibrium be, right? What will the condition for static equilibrium? So if I have more than one particle, can erase this to look at say two particle system, like a dumbbell or something, right? So say I have a two particle system. So imagine I have a particle here, still kind of wet. So if I have a particle here and another particle here, so this is, say, M1 and M2. This may be two people, for instance, and I'm thinking them as particles. So there may be forces on this, whole bunch of forces on this, and then maybe this guy's attractive force between them, it will be like that. So these are the forces on one. So when I add these guys up, let's call this forces on one, is add up F1, F2, F11, F12, F13, F14. So if there are like 4 forces, it's going to add up like that. Let's call this F12 and let's call this F13. So this is by 2 on 1, and this is by somebody outside. So these forces, these are from external to system, by objects external to system, because this one is from, these two are forming my system 1 and 2. The same kind of stuff will be over here, and so force, let's call them, and then there will be F21 will be that way, just exactly opposite turns, and so you will have F2. So all of this added up will be F2. So if I go back to F1, I see all these forces which are external, and then there is the internal. So we're gonna try to write this a little bit so that each force is so F1 is some external parts like this guy, this guy, this guy, that will go in here, and then you'll have F1, and this is internal. So this one stands for that. So this is F1, and F2 will be the same way. F2 will have things from outside 1, other than 1, and then it's going to be F2 internal, and that's this force. So we can write like this. This is called separating all the forces that's acting on one into the source, external or internal. So what's the equilibrium for this system look like? It says neither A nor B, neither 1 nor 2 should accelerate. So neither M1 nor M2 can accelerate, which means this force by itself is 0, and that means F1 is 0 and F2 is 0. So these are the forces on 1, all the forces on this. So this is the net force on 1, on M1, and this was net force on M2. Well, if I separate them out, so this I can also write as F1 external plus F1 internal, and this internal is just from the other particle, equal to 0. So I can write this guy also F1, F2 external. So external is everything other than 1, okay, and F2 internal, and this is by the 1. Well, guess what? If I add these two guys, then I see there will be these two internal guys and then these guys external guys. So let's keep them separate. F1 external plus F2 external. Making sense, right? I mean, if I just keep them together, right now the punchline is coming. F2 internal, that's equal to 0. But Newton's third law says that this force is exactly opposite of that force. So this one is the force on 1 by 2, F on 1 by 2, and this is F on 2 by 1. And guess what? When you add them up, this is exactly opposite of each other. So so their sums should be 0. Third law, So although individually this must abide by, but I can see there's a simplification here, which is all the external forces, F1 external plus F2 external external equal to 0. So this is the net external. F on system now, regardless of whether 1 or 2, all the net external, right? It's a net external is equal to 0. So this is an important simplification that came from here, and this is what we implement. Okay, so that's one of the rules we can discover. Another one we can discover, which I'm not going to show you, is if I look at the torque by all these forces. So then I don't need to look at internal forces either. If you look at the torque, net external, and we can look at the vector. So depending on the axis I pick, directional axis, and I can pick any pivot I like. Turns out when this is 0, then I can pick any pivot I like, and that will also be 0. So this simplification of using only external forces got deduced from here, but these are the two principles that will guide us in setting up problems, understanding what's going on in a large body. So I would like to illustrate this now with an example. Okay, so let me move to another video where I'll go through the example, some examples of objects in static equilibrium and kinds of relationships that you can deduce based on these principles. Okay.